Somewhere in what is now the northern Great Plains of the United States, a Triceratops was alive. Not millions of years before the end of the Cretaceous. Not hundreds of thousands of years before. Thousands of years, possibly tens of thousands. Not millions. The fossils sit just below the line, not millions of years earlier, just below. We know this because of where the bones were found. In the geological record of the Hell Creek Formation, a sequence of rock strata stretching across Montana and North Dakota, the fossils of the last non-avian dinosaurs lie within meters of a thin, distinctive band of rock. That band is called the Cretaceous-Paleogene boundary. It marks a single moment in Earth's history, the moment the asteroid hit. And the fossils of Triceratops, Tyrannosaurus, and their contemporaries are found just below it, close enough that, measured against geological time, the distance is almost nothing. Those individuals did not die out slowly. They were alive and then they were not. In 2019, a team led by Tyler Lyson of the Denver Museum of Nature and Science published a landmark paper in the journal Science, providing the most detailed, time-calibrated continental record of the first million years after the mass extinction ever assembled. Their data, and the broader Hell Creek stratigraphic record it draws on, gave us the most precise picture ever developed of how close to the boundary the last non-avian dinosaurs actually were. What that picture shows is not a gradual fade. It shows an ecosystem at full capacity right up to the line. These fossils don't just record the end of the dinosaurs. They record how close to the final moment some of them got and what that proximity means. But to understand what those meters mean, you first need to understand the ground those fossils were sealed in. To read the last chapter of the dinosaur era, you need to understand the book it was written in. The Hell Creek Formation is a sequence of rock strata, mudstones, sandstones, and siltstones that stretches across portions of Montana, North Dakota, South Dakota, and Wyoming. It was deposited over roughly 2 million years during the final chapter of the Cretaceous period by ancient river systems flowing across a broad subtropical floodplain. The rivers shifted, the sediment built up, organisms died and were buried. And layer by layer, the record was sealed. Every layer is timed, sometimes fast, sometimes slow, but always in order. Read the stack from bottom to top and you are reading the past. The Hell Creek Formation is one of the best terrestrial records on Earth for the final chapter of the dinosaur era. As paleontologist Stephen Brusett of the University of Edinburgh and colleagues noted in their 2015 comprehensive review in Biological Reviews, the Hell Creek is one of the most studied terrestrial sequences for understanding what happened to non-avian dinosaurs in the last 2 million years of the Cretaceous. The Hell Creek Formation preserves an unbroken stratigraphic sequence, dinosaur-bearing layers below the KPG boundary, then the boundary itself, then post-extinction Paleocene layers above. Continuous, ordered, readable. The fossils found in this formation include Triceratops, the most common large dinosaur in the record, comprising roughly 40% of large dinosaur specimens identified in systematic surveys of the formation. Also Tyrannosaurus rex. Also Edmontosaurus. Ankylosaurs, ornithomimids, early mammals, turtles, crocodilians. The characteristic dinosaur fauna of this late period, what paleontologists call the Lanchian fauna, has been found in some sections of the formation as close as a few meters below the KPG boundary. As Johnson, Nichols, and Hartman documented in their 2002 Hell Creek synthesis for the Geological Society of America, the Lanchian fauna is present in the fossil record right up to the KPG boundary, not trailing off a million years before, not fatting out over hundreds of thousands of years. Present. A few meters of rock, that is the entire measurable buffer between living and gone. That boundary layer is one of the most precisely dated events in Earth's geological history, and the precision is what makes this story matter. To read this rock at this level of resolution, you need someone who has spent a lifetime learning its language. His name is Tyler Lyson. He is a paleontologist and curator at the Denver Museum of Nature and Science in Colorado. He grew up on a ranch in North Dakota, Hell Creek country, where he was finding dinosaur fossils as a child. He completed his doctorate at Yale University and has published extensively on the Hell Creek ecosystem, from dinosaurs and turtles to the recovery of mammalian life after the extinction. He is one of the people on Earth who knows this formation most intimately, not just as a scientist reading data, but as someone who has been reading that rock his entire life. He doesn't just study the end of the dinosaur era, he grew up in the ground where it happened. That personal familiarity matters. The best fossil science is often done by people who have spent years, sometimes decades, in a single formation. The 2019 paper led published in Science and co-authored with researchers from the Denver Museum of Nature and Science, the Smithsonian Institution's National Museum of Natural History, the University of New Hampshire, Wesleyan University, and the University of Maryland, was primarily a paper about what came after the extinction. It mapped, with extraordinary temporal precision, the first million years of mammalian recovery following the KPG event, showing how mammal body size and diversity rebuilt themselves in the immediate aftermath of the catastrophe. His primary field site for that recovery work is Corral Bluffs in Colorado, the Denver Basin. That's not Hell Creek in Montana, but it's calibrated to the same boundary event, and it's part of how scientists translate layers of rock into precise spans of time. The Corral Bluffs framework and the Hell Creek record are different sections, correlated to the same global boundary layer. And to build that framework, the team had to establish exactly where the boundary sat. They had to calibrate the rock to know, within thousands of years rather than millions, where the impact layer sat relative to every fossil in their sections. In doing that calibration, combined with the broader Hell Creek synthesis literature, the science confirmed what had been suspected but never this precisely stated. The characteristic dinosaur fauna of the Cretaceous, Triceratops, Tyrannosaurus, the whole assembly, is present in the fossil record right up to the boundary. Not fatting away a million years before, present, and then above a thin layer of pale clay gone. But what exactly is the KPG boundary layer, and what does it take to know with this precision what it marks? The boundary isn't a metaphor, it's a physical layer of rock, and it carries its own evidence. There are three physical markers in the KPG boundary that matter. Three independent lines of chemical and mineralogical evidence, each pointing to the same moment. The KPG boundary is marked globally by a thin band of clay, sometimes just a centimeter or two thick, that contains anomalously high concentrations of the element iridium. Iridium is rare in Earth's crust. It is far more common in asteroids and comets. The global presence of this iridium layer, found in marine and many continental rock sections worldwide, was first identified by geologist Walter Alvarez and his father Luis Alvarez in 1980, providing the first physical evidence of an extraterrestrial impact at the KPG boundary. The same chemical signature in the same time slice found globally, that is not a local event, that is a global one. In the same boundary clay, scientists have found shocked quartz mineral grains that show microscopic deformation features called planar deformation features, produced only by the extreme pressures of a hypervelocity impact. No volcanic eruption generates this signature. Only an impact does. Shocked quartz requires impact-level pressures. This signature is tied to hypervelocity impacts, not volcanism. The boundary also contains glass spherules, microscopic beads of rapidly cooled impact-melted rock, ejected globally and rained back down onto Earth's surface in the hours following the Chicxulub impact. These microtectites are chemically matched to the Chicxulub impact site on the Yucatan Peninsula. Together, iridium anomaly, shocked quartz, glass spherules, three independent physical signatures, globally distributed, chemically and mineralogically linked to a single impact event, in the same centimeter-thick layer of rock. This is not a theory, this is a layer of rock you can point to. Above the impact markers, not within them, but above, the biological record writes its own chapter. Immediately above the iridium layer, the pollen record collapses. The diverse assemblage of flowering plant pollen and conifer pollen that characterizes the Cretaceous drops sharply. In its place, an overwhelming surge in fern spores. This is the fern spike. Ferns are pioneer colonizers, the first plants to re-establish after catastrophic disturbance. Their spores are hardy, their root systems aggressive. After the impact, when most flowering plants had died back or gone regionally extinct, ferns moved in first. The fern spike is found in KPG boundary sections across North America. It is not a chemical marker of the impact itself, it is a biological record of the ecological aftermath. Below, Cretaceous forest diversity. Above, the first response of a damaged world. Below the line, a diverse Cretaceous forest. Above it, ferns taking over a world that had just been remade. The transition is not gradual, it is a sharp boundary in the pollen record. The KPG boundary has been dated with extraordinary radiometric precision. Paul Wren of the Berkeley Geochronology Center and colleagues, in a 2013 paper in Science, established the age of the Chicxulub impact at 66.043 plus or minus 0.011 million years ago, using argon radiometric dating of impact glass, tektites from the boundary layer itself. The uncertainty in that date is approximately 11,000 years. In geological terms, that is remarkable precision. In human terms, it is still a span longer than the entirety of recorded history. We cannot date a Triceratops fossil directly to within 1,000 years. What we can do is measure how many meters of rock lie between that fossil and the impact layer, and convert that distance into time using known sedimentation rates, calibrated against the boundary age. So what was that world actually like in those thousands of years closest to the line? The fossils don't just tell us these animals existed, they tell us what world they were living in right up to the moment it ended. The data does not show a dying world, it shows a functioning one. This picture is not imagination. It is built from thousands of fossils in a single ordered stack of rock, cataloged across decades of systematic excavation in Montana, North Dakota, and South Dakota. Mud underfoot, river air, ferns, and conifers sweating in heat. The Hell Creek environment of the late Maastrichtian was not a collapsing ecosystem. The fossil record shows a fully functioning community. Large herbivores, apex predators, small mammals, reptiles, and birds, all represented by specimens found in the uppermost layers of the formation. Triceratops was the most common large animal in the formation. Tyrannosaurus rex was the apex predator, present in census counts across multiple sites. Edmontosaurus formed large herds on the floodplains. Below them, turtles in the rivers, crocodilians in the waterways, lizards, frogs, salamanders. And in the undergrowth, small, shrew-sized mammals, the early ancestors of the lineages that would eventually inherit the Earth. This was not a world in collapse. This was a world at full ecological capacity. For decades, scientists debated whether non-avian dinosaurs were already declining before the asteroid, whether the impact was a final blow to a weakening lineage, rather than a catastrophic end to a thriving one. Brusset and colleagues' comprehensive 2015 review in Biological Reviews addressed this directly. Their analysis found little support for a global, long-term decline in non-avian dinosaur diversity in the final period before the K-PG boundary. The pattern in the Hell Creek Formation does not support the conclusion that dinosaurs were dying out on their own. The data that superficially looks like a decline is better explained by sampling bias. The uppermost layers of any geological formation contain less fossil material simply because less time has passed for fossils to be exposed, eroded, and found. That is not evidence of a decline. It is an artifact of how fossilization works. The Triceratops specimens found closest to the K-PG boundary were not survivors of a failing species. They were members of a thriving population, a population that had no warning of what was coming. We even have evidence from a site in North Dakota of what the Hell Creek world looked like in the hours immediately after the asteroid hit. The Taney site, described in a 2019 paper in PNAS by Robert De Palma and colleagues, preserves a chaotic layer of sediment interpreted as a rapidly emplaced surge deposit triggered by seismic waves from the Chicxulub impact arriving in North Dakota within minutes of the strike on the Yucatan Peninsula. The deposit contains fish carcasses, impact ejecta glass matched chemically to Chicxulub, and spherules embedded in the gills of fish, consistent with animals asphyxiated in the first rain of impact ejecta returning to Earth. This is not a record of the last day before the asteroid. It is a record of the first hours after it. The interpretation of Taney's has been subject to ongoing scientific discussion. The core peer-reviewed finding, a rapidly deposited ejecta-bearing bed in Hell Creek, consistent with immediate post-impact emplacement, is supported by the published evidence. Taney's doesn't show the last moment of the dinosaur era. It shows the first moment of what came after. And in that gap, between the functioning ecosystem below and the chaos above, is the entire weight of what happened. But to understand precisely how close those fossils were to the boundary, you need to understand how scientists actually measure it. The science isn't we found a bone near a layer. It's a measurement, and measurements require tools. The claim that certain dinosaur fossils lay very close to the boundary, thousands, possibly tens of thousands of years before the impact, is not a loose estimate. It rests on three converging lines of physical evidence, each independent, each pointing to the same conclusion. The K-PG boundary in the Hell Creek Formation is a physical layer you can locate in the field. It is identified by the iridium anomaly, the presence of shocked quartz, and the sharp pollen transition, the fern spike that begins directly above it. In some Hell Creek sections in Montana, the K-PG boundary sits at the contact between the Hell Creek Formation and the overlying Fort Union Formation. In North Dakota, it sits within a few meters of the formation boundary in some sections. Locally variable, but physically present and chemically identifiable wherever it is found. You can walk up to it, you can put your finger on it, you can say, here is the Cretaceous. and not 1 centimeter above this point. Sedimentary rock accumulates at measurable rates. Those rates can be estimated using dated horizons, volcanic ash layers, and other datable events in well-calibrated sections that are carefully correlated to the boundary sequences we're studying. Tyler Lyson's Corral Bluff section in Colorado, his 2019 science paper and the companion chronostratigraphy study by Fuentes and colleagues, used uranium-lead radiometric dates to build one of the most precise temporal frameworks for a KPG continental boundary section ever assembled. That framework, along with comparable work in sections that preserve the same boundary horizon, is what allows the conversion, meters of rock into spans of time. The exact number of years per meter varies by location. River systems deposit sediment at different rates depending on flood frequency, sediment load, and channel migration. But the conclusion is robust. The fossils are very close to the boundary. The exact proximity depends on the specific section and the sedimentation rate applied. What the stratigraphy consistently shows is that the Lanchian fauna, the full complement of dinosaurs characteristic of the latest Cretaceous, is present within the uppermost meters of the Hell Creek record, right up to the impact horizon. The final piece of evidence is the position of the fossils themselves. Triceratops, Tyrannosaurus, and the other characteristic Hell Creek dinosaurs have been recovered from the uppermost stratigraphic layers of the formation, close to, and in some sections as close as a few meters below, the iridium boundary layer. As the Hell Creek synthesis literature documents, Johnson, Nichols, and Hartman 2002, Fastovsky and Berkovich 2016, Brusset and colleagues 2015, the characteristic Lanchian dinosaur fauna is present right up to the KPG boundary. There is no gap in the record that would suggest these animals had disappeared substantially before the impact and left an empty landscape. The most parsimonious interpretation: these animals were alive in normal population densities when the asteroid arrived. But here's what all this precision actually means for how we understand the end of the dinosaurs and why it matters. Right up to the line is not a poetic phrase. It is a stratigraphic claim, and it changes the story of how the dinosaurs ended. Let's step back and ask the bigger question. Why does it matter whether the last non-avian dinosaur fossils are found a few meters below the KPG boundary versus hundreds of thousands of years below it? It matters because proximity is an argument. If the dinosaurs were already declining long before the asteroid, the impact may have been the final blow to a weakening lineage. If they were thriving right up to the boundary, the asteroid was everything. Some researchers have argued for a gradual decline in dinosaur diversity in the final stages of the Cretaceous, driven by climate cooling, the volcanism of the Deccan Traps in India, or ecological disruption from sea level changes. Others have argued for a catastrophic impact-driven end. The Hell Creek stratigraphic record, and particularly the proximity of the Lanchian fauna to the boundary, supports the abrupt end interpretation. Not without ongoing scientific debate, but the weight of the evidence from Hell Creek, as Brusset and colleagues assessed in 2015, does not support a protracted pre-impact decline. What right up to the line means in plain language is this: it means there wasn't time for evolution, adaptation, or escape. Only impact. The most parsimonious reading of the data, these were not the last survivors of a failing species. They were a functioning population ended by an event with no biological precedent. The significance of the Lyson 2019 paper is not just the proximity question. It is the recovery record it builds on the other side of the boundary and the precision with which it does it. Within approximately 100,000 years after the extinction, mammalian species richness doubled in the Corral Bluff section. Within 300,000 years, mammalian body mass had tripled and dietary specialization had emerged. Within 700,000 years, the first legumes appeared, coinciding with the arrival of larger, more diverse mammals. These are not vague estimates. They are time-calibrated data points in the most precise continental recovery record ever assembled. And they begin from a defined zero point, the KPG boundary, the same boundary that the last Triceratops fossils were found just below. Which means we can now reconstruct, with real scientific confidence, what those last moments of the dinosaur era looked like, on the ground, in the rock, in the world they were living in. Everything we've described is measurable, but measurements can be given a face. In the final thousands of years of the Cretaceous, in the stretch of time represented by a few meters of mudstone in the wind-carved badlands of Montana, a Triceratops was alive. It was not the last of its species. Triceratops was abundant, the most common large dinosaur in the formation, roughly 40% of the census in systematic surveys. It was a species at its ecological peak. And somewhere in those last thousands of years, an individual in the herd died, on a floodplain near a river. It was buried by sediment, the ordinary accident of preservation. It became a fossil. And eventually, those sediments became rock. And the rock built up layer by layer until another thin band was deposited on top of everything. A pale, iridium-rich clay carrying the chemical signature of an asteroid that had just hit the Yucatan Peninsula 3,000 kilometers to the south. The Triceratops fossil is below that layer. Everything above it is different. Right up to the line, not millions of years before it, right up to it. On one side, a world that had been dominated by non-avian dinosaurs for 160 million years. A world of Triceratops herds and Tyrannosaurus hunting grounds and hadrosaur migrations across subtropical floodplains. A world that had survived every previous extinction event. A world that, by every available measurement, was not in decline. On the other side, the fern spike, the silence. 100,000 years of slow mammalian rebuilding, documented in Colorado mudstone by Tyler Lyson and his team, the beginning of the world that eventually produced us. The distinction between those two worlds is not a gradual geological transition. It is a line. And on one side of that line, the last non-avian dinosaurs that ever lived were doing exactly what they had always done, moving through a forest, feeding, living, with no knowledge of the rock falling toward them from space. The difference between before and after is a layer you can touch. A line in rock, a world in ruins. That is what the meters mean. That is what right up to the line means. The fossils found near the K-PG boundary cannot be directly dated to within thousands of years. The proximity inference is based on stratigraphic position relative to the dated boundary layer and sedimentation rate estimates from correlated sections. It is a well-supported scientific inference, not a direct radiometric date on the fossils themselves. We cannot identify specific individual animals from the uppermost Hell Creek layers. We cannot say with certainty whether those uppermost fossils represent peak population density or scattered survivors. The fossil record preserves what was buried, not a census of what was alive. What the record does support, with strong stratigraphic and taphonomic evidence, is that non-avian dinosaurs were present in the Hell Creek ecosystem right up to the K-PG boundary, and that there is no evidence of a substantial pre-impact decline in the latest Cretaceous layers. The science is clear, the picture it paints is extraordinary. Next video, what happened in the 100,000 years after the asteroid, and how the mammals that inherited the Earth got there. The Lyson 2019 data tells that story in extraordinary detail. If you like videos that rebuild ancient worlds from real geological evidence, subscribe.